So, hello again, guys. I like to see that there are still some people that are here, even if the Open Fest is closely moving towards its end. And now Viktor Kirilov will talk to us about the modern programming language, NIM. Applaud him, please.
Hello, everybody. So today we'll be talking about NIM and why it makes sense to call it C++ 2.0 or something like that. So a little bit about me. I'm a native. I made the fastest C++ testing framework. I implemented a little bit of functionality in the NIM compiler. I write C++ for a living, sadly, and I like really text-heavy slides and reading from them with lots of bullet points. Sorry. So today we'll be introducing NIM, features, metaprogramming, examples, compilation model. Then I'll talk a little bit about the web, the garbage collection, and the runtime, a comparison with C++, and some closing thoughts. So let's get on with it. This is NIM, and its logo is a crown because it's meant to be the one language to rule them all. And a little bit about it. It was started in 2005, yeah, by Andreas Rumpf. It's a strongly typed, compiled, multi-paradigm, indentation-based language. And it has some of the most powerful metaprogramming out there. It's meant to deliver the speed of C, the elegance of Python, and the power of Lisp and Perl. And it's backed currently by only one sort of big organization, one of the top 100 cryptocurrencies. And yeah, it really aims to dominate the space in programming languages, and because it compiles to C, C++, JavaScript, Objective-C, it can basically run on any platform. And lately, it has been gaining prominence in game development. So, this is a really simple Hello World program. We compile it, we execute it, and we get a Hello World in our terminal. And this is what a little bit more NIM code looks like. As we said, it's indentation-based, like Python. At the top, we're importing a module. Then we define inside of a type section a person object, which has a name and age. Then we make an array with a few people inside of it. We also define a function called do work. It's called a procedure. That's how we name functions in NIM. And inside of it, we iterate over all the people, and we print them one by one. So nothing really unordinary, looks like Python, mostly. But let's go through a bunch of selected features which are really hard in other languages to achieve, but in NIM they come basically for free. For example, if you want to implement distinct types, like we want to implement a units library, or we want to implement a currency, in NIM we can just say that dollars is a distinct float. It's basically a float underneath, but it's a distinct type. And then we can decide to borrow either some of the operators which work for floats, or even all of them with just a single line. And then we have type safety when dealing with currencies. Nice feature which, when dealing with C++, requires hundreds, if not even thousands of lines of code and templates just to implement a nice behaving integer-like class for something. Iterators. In this case, we're defining an odd iterator, an odd numbers iterator, which basically will print all of the odd numbers in a sequence, and we can use it in a for loop. It's inline and it's mostly performant. We can also have closures which are actually stateful So closure iterators, they have state with them. They're a resumable function which can be passed around, and the state can be preserved inside of it. And in this case, we can pass the count function into the invoke function, which accepts a closure iterator, and it can use it inside of it. Anyway, the idea here is not to really dive too much into these features. We'll show a lot more examples in the metaprogramming part. So another thing which is quite hard to do in C++ in a nice way is discriminated unions. For example, stud variant is thousands of lines of code. It doesn't really generate optimal code at runtime. People constantly blog about that stud visit is kind of slow sometimes. And in NIM, discriminated unions are they're part of the language. And in this case, if we want to model an abstract syntax tree in the NIM language, what are we going to need? We're going to need an enum, an enumeration to distinguish different types of nodes, and also a node class, I mean, in this case, a node object, which, depending on the type of node it is, it will have different fields. So here in the middle of the slide, we're saying that we have a node type, which, depending on the kind, which is the node kind enumeration, if it's an integer, it has an integer value. If it's a string, it has a string value. If it's adding or subtraction, then it has a left and right nodes. And if it's an if statement, for example, it will have a condition, a then part, and an else part, which are also nodes. And then when we create a node and we give it that it's of type integer and an integer value, accessing the string value is a runtime error because it's constructed as an integer value. And this is provided by the language instead of trying to implement it in thousands of lines of code in C++, for example. How is object orientation and OOP done in NIM? Well, as we can see, types don't have methods in themselves, but we're defining procedures and methods outside of the types. And always the first argument to the procedures and the methods is the actual object we'll be working on. And another thing is that most languages which have modules, they by default export everything. But NIM by default doesn't export anything from a module. You have to be explicit what gets exported. So if you want encapsulation with NIM, basically you define your type along with the procedures which work on it in a module, and you export only the relevant parts outside of that module, so it can be imported and used. Also, NIM has uniform call syntax. So even though all of the procedures and methods, they take the object as a first parameter, actually we can call object.function instead of only function with an object passed to it. In NIM, if you want to have dynamic binding, basically polymorphism, you gotta use the method keyword. And then if the argument is a polymorphic type, then it will call the right function. So one other really cool thing about NIM, which also has a lot in common with the build system of NIM and the way it's actually compiled, is the effect system. And so, for example, here we have two functions. Write to console, which basically has an I/O operation. It tries to stud out. We also have a touch global function, which touches a global variable. If we want to define a function called, in this case, impossible, and we annotate it with the no side effect that means that the compiler will statically check at compile time that none of the functions it calls transitively ever has any side effects. So in this case, neither of the two functions can be called. And even if these functions were defined in a module outside of the current one, it would still be checked at compile time, and the compiler can enforce if something really doesn't have any side effects. We can also annotate which exceptions are meant to be raised by a function. And if there is any other function call anywhere in the whatever that function is doing, which can raise another exception, this won't compile because it's going to be checked at compile time. We can also constrict it to say that we don't want any exceptions to leave outside of this function. We can also use custom tags, and we can leverage this effect system in any way we want, actually. And for example, a function can be deemed garbage collection safe if it doesn't have any side effects. And so the garbage collection and the effect system play nicely. So a little bit about metaprogramming. The idea behind is that metaprogramming is when you actually write a program which reads, generates, analyzes, or transforms other programs. And the idea why we'd want to do it is basically one reason is to optimize code. For example, to have some compile time rewrites. In C++, this is done with expression templates. We can also enforce better coding patterns, and usually we can really increase code readability and maintainability. But of course, we have to be careful because we might build the wrong abstraction, for example. And in the case when the language which we use for metaprogramming is the actual language which is the final program, that's called reflection. So first of all, what's an AST? For example, we have this program on the left, which is basically some algorithm, a while loop, and a return statement at the end. The abstract syntax tree is actually the representation of this program inside of the compiler. That's what the compiler builds as a tree structure when it parses your source code, because any program can be represented as a tree. And in this case, we have a statement sequence because we have two statements, a while and a return. The while statement has a comparison, and it also has a body. Inside of the body, we have a branch, which has a condition, an if body, and an else body. I guess you get the picture. So in NIM, we can say that there are 4 levels of complexity, like normal procedures and inline iterators, nothing special about them. We also have generic procedures and closure iterators, which are more high level. We also have templates and macros, which are the metaprogramming part in NIM. And templates, they basically expand and replace AST nodes, and macros can manipulate the AST in almost any way. They also respect the type system, unlike some other things such as the C preprocessor. And the thing which actually does all the substitution and all the evaluation of compile time is the NIM virtual machine. So it is precisely responsible for the expansion and execution of templates and macros, and also about the compile time evaluation of code, expressions, constant folding, and stuff like that. So this is our first example of a template. At the top, we've defined a with lock template, which gets a lock, and also a body, which is untyped. That is going to be a block of code, which we actually receive. And inside of this template, we acquire the lock, and then we put whatever the body is inside of a try block. And then, finally, we release the lock. In the middle snippet, when we actually use this template, we use it just like a normal construct in the language, and we call with lock, with our lock, and we pass a bunch of code inside of it. And that, after the substitution, will end up looking like the code at the bottom. We have a lock, we init it, we acquire it, everything which was passed to the template is now in the try block, and we finally release the lock. Another example of a template is, for example, this with file, where the usage is at the bottom, and ideally we would like to name what the variable will be using, what the file will be called, also what file we want to open and how we want to open it. And the template receives, again, the name of the variable it's going to create, the file to open, the open mode, and again, a block of code which should be executed while the file is open. Here, we cache the file name into a local fn variable. And the reason for that is because this template is, wherever we use it, is actually not a function call. So if we have passed a function which generates the string for the name of the file, and if we use that thing inside of the template in more than one place, we'll actually end up calling that function more than once. So that's why here we have to cache the file name once at the beginning of the template, and then use it when we're opening the file, and also in the quit statement if there's an error in the opening of the file. And again, whatever the body is of the actual template, whatever we have passed as code, ends up in the try block, because that's where we've put it. A little bit more examples. In this case, we have written a rule which basically pattern matches in our source code if anywhere we are multiplying an integer by 2. And in that case, this template gets automatically triggered. So we can rewrite every multiplication of an integer by 2 as just summing that integer with itself once. We can do something else. We can break the language if we want to. But again, the point here is to illustrate the power of the language and what it can actually do. Because any modern compiler, because NIM compiles to C, and then we pass the C program to the C compiler. Of course, they're going to handle an integer multiplication by 2, and if it's more optimal, they're going to write it to adding it with itself. But here again, the point is to illustrate what can be done with NIM. And also, the not equals operator, template, is defined in terms of equality. And that's actually what is being done in the system module with NIM. Because that's a really nice way to reuse code. The next thing we're going to talk about is macros. In this case, we have a toEnum macro, which receives a string and does some things. Let's see how we use it. In the type section, where we want to define an enumeration, the enumeration is called color, and we call toEnum, and we pass it a string with enum values. And that, during compile time, takes that string, we split it by white space, and then we iterate over separate words, and we generate a new identifier, which we add to the tree enum we have actually, to the tree AST node we have created, which is of type enumeration. So in the macro, we make a new tree AST node, we set it to have a type of enumeration, and then we add a bunch of identifiers to it. And then after this type section, where we have actually called the macro, we can use those identifiers as if they were written by hand. They're now valid code. We can also do some other cool stuff, like in this case, we can call dump tree on a code of block. And in this case, this code of block is making a new variable of some type, and it's initialized with some constructor. And the output of this code would be something like this. We have a statement list which has a single statement, which is the var section, and inside of it there are a few identifiers, which are the name of the variable and also the type, and then there's an object constructor. So we can inspect the AST which the compiler sees of our program, and we can inspect it so easily. But we can do some other cool stuff, like we can call dump AST gen on a code of block. That's part of the macros module. And in this case, the code of block is defining a procedure, a function, which basically prints stuff to the console. And dump AST gen is not going to give us the representation of the AST, but it's going to dump us the NIM code, which would be necessary to generate that code. So that's a really nice and easy way to, if you're wondering how to write a complex macro, and you know how the final result should look like, you can dump the AST generation required for it, and then figure out how to finish your macro. So if we take this output from dump AST gen of this procedure, and we actually put it in a macro, and then we call that generate hello macro, now the function hello is visible. It's usable. It's already created during compile time while the program is being compiled by the NIM compiler. We can do some really powerful stuff, like we can define a DSL, which is a domain-specific language, for example, for HTML. So instead of using separate tools for templating and generating our HTML and whatever, we can do all of that inside of our NIM source code with the HTML DSL package from the package manager. And this is going to be the final result after calling render on the page. We can do even yet more crazy stuff at compile time. Like usually when we're dealing with protocol buffers and other such tools where you define once the structure of your objects, and then you generate a bunch of bindings to different languages so they can communicate and use the same objects, but you don't want to write the code which constructs those objects in every language by yourself. So that's why usually for such technologies like protocol buffers, you have a generator which, based on the description, generates the bindings for each language. But in the case of NIM, we can actually implement a parser of the specification of protocol buffers or protobuf, and we can, at compile time, parse the string. And here, when we're calling parse proto, we're actually parsing the string we've passed it, and we even generate the necessary types and even functions to deal with those types at compile time. So now we can use those messages as native types inside of NIM. And we don't need any separate build steps. This is right here inside of our NIM source code. So what does metaprogramming give us? Well, much higher levels of abstraction. It can help us enforce, again, better patterns, more readability, and maintainability. And it can help us with the creation of DSLs, such as the HTML example we just saw. And for example, if you're dealing with a nasty GUI library like Wix widgets, which is great, but dealing with it is not that trivial, you have to write a bunch of code, you can simplify that based on your needs and write your own DSL language based on with just a few templates and maybe a few macros. With NIM, you can do away with any external code generation and templating engines. And remember the last time you had to write a serialization function and you had actually forgotten to serialize a field? That again can be automated with NIM. You can iterate at compile time through all of the fields inside of a type and just call serialize on each of them. That's not code which should be written by humans, it should be automated. And as a really nice example about the power of metaprogramming in NIM, the asynchronous I/O framework based on async and await is implemented entirely with metaprogramming. And instead of having it built into the language, it just leverages the coroutines which are present by the language and builds on top of that to implement the async and await semantics with macros. It's basically a DSL for async and await. Some other cool features, like parentheses are optional when you're calling functions. You have destructors since recently. You have generics, so you can write your hash set and it can deal with any kind of types. You have concepts, you have pattern matching, implicit conversions, converters for implicit conversions. So we're actually explicit when we want something to be implicitly convertible. Also an extensible pragma system, defer statements, exceptions. One thing I really like is the discard keyword, because in NIM, if a function is returning a value, and if you just call that function but you don't store that value anywhere and you don't do anything with it, that's an error. You have to be explicit about discarding the result of that function. So that's just yet another example of good defaults in the language. And that, for example, is something which is now they're trying to add it in C++ with a no discard attribute, which actually works. But again, this is from the start in the language itself in the case of NIM. And it also has a package manager, unlike some other languages like C++. So let's see how NIM is compiled. In this case, we have three modules: main, foo, and bar. Main imports foo imports bar. In bar, which is on the right, we see that from bar has an asterisk after that. That's how we decide which symbols should be explicitly exported from that module. So local from bar is not visible from anywhere else, but from bar is actually accessible from whoever imports bar. So if we want to compile this program, we actually call a compiler NIM, and we only give it the root module, which is in this case main. And then the compiler will automatically follow the imports and actually determine which modules are necessary. And that's how, when the NIM compiler is compiling the NIM program, it actually has the whole view of the program, because we're not compiling each module separately. We actually compile only what's necessary based on what is being referenced from the main module. And the NIM compiler does whole program analysis, and that's why it can effectively and easily track, for example, the transitive guarantees of the effect system. And when we decide to run this program, we also see that it doesn't have a main function. And even the full module has code in the top-level scope, and even it will be executed. And the order works something like this. In the main module, at the top, we import full. That means that if there's any top-level code, it should be inside of full. It should be executed before the code in main. So we go to full. We also see an import of bar. Bar has nothing in its top-level scope except for initializing a local variable. Then we return to the initialization of full. We see that at the bottom, we have an echo statement. We echo full. Then we continue with our main module, where we call from full, which actually prints bar, which is defined in bar and is referenced by full. And at the end, we also print main, because it's at the end of the main module. This is basically a depth-first search traversal, and it's strictly guaranteed, like what the ordering is strictly guaranteed, unlike in C++. Like if you have a bunch of globals in C++ in different translation units, you have no guarantees which will be initialized before the others. But in NIM, this is strictly defined. So whenever we compile a project in NIM, we actually always compile the root file. And For example, the NIM compiler is comprised of 140 files, and it also references a bunch of the standard library, which is shipped along. And the entire compilation of the entire NIM compiler, the NIM part, takes around 4 to 5 seconds on my machine. After that comes the compilation of all of the 150 or 200 source files, the C source files, which are produced for each module, and that takes a bit more, but the total compilation of the entire NIM compiler on my machine currently is 20 seconds. And that's pretty awesome, and that's in a release build. And one thing which the NIM community will be working on in the future is incremental compilation. So even though you always issue the command to compile the project from the root, eventually we'll get to the point where only the changed modules will have to be reanalyzed and reparsed and whatever. And only other modules which are affected by those will also have to be reanalyzed. Eventually, these 4 to 5 seconds of compilation in the NIM compiler will be dropped even further. And one more thing which I forgot to mention is that for each source file for each NIM module, we end up having a C source file. But based on whatever is referenced, so if some module exports 10 symbols, but another module imports that module and uses only 2 of those symbols, only 2 of those symbols will end up in the final binary. They won't be, especially in the module which imports the other module, it won't have forward declarations for every other exported function. It will forward declare only whatever is really necessary. So every source file which gets compiled for every NIM module, they all end up in the NIM cache folder. That's like a temp folder where we store all intermediate files. And each of those source files actually includes a common header called NIM base, which defines a bunch of common platform-specific macros and stuff. So the code generator of the NIM compiler, which generates the C code, has to generate it in a single way, but then this header wraps the platform-specific differences in macros. So when we define a function in NIM and then we call it, the result looks something like this in the C code. First, we have a bunch of structures which define the string sequence, whatever. That's not really important at this point. Actually, I should mention that each source file is structured in the following way. At the top, there are the includes. Next, there are some type definitions. After that, we have forward declarations of whatever is necessary, both within this translation unit and if it's coming from somewhere else. And after that come the definitions of the actual functions which are defined in this source file. And only at the end we have the initialization code which is being done at program startup. So in this case, for the full function, we see that actually there are really horrible symbols generated. That's because of mangling, because based on the return type and the argument type and whatever, this is a common way to mangle names in programming languages, especially C++. So C++'s mangling is not like a hash like in this case. You can actually reason about the mangling in C++. You can infer if it has 4 arguments or 2 and also what types of arguments they are. But in NIM, mangling is just a hash. But anyway, so at some point here in the source file, we have the literal hello, which is a string literal. At some point later, we have a forward declaration for the full function, which is just a forward declaration in C. Then we have the definition of full. And at the end, somewhere in some initialization code in the whatever should be executed in the main scope is, we have a call to full. And it's just C code. Here we have a definition of a type, which has an integer and a Boolean inside of it. We also have a function which returns an object which is constructed with specific values. And then we call that constructor and we echo the answer. Again, only a part of the final source file will look something like this. Our structure, our type, is just a regular C struct with only the fields we actually told it because it's a really straightforward type. The function which constructs our object is, again, nothing too special. We have a result of the type, we set the specific fields, and then we return it. And the usage is, again, nothing out of the ordinary. This is C code. Resumable functions, in this case, closures. They are also implemented in terms of only structures and pointers in C. And for a closure, we need two things. One of them is the definition of the state. In this case, we have an int colon state, which tells us how far along we've reached in the resumable function, at which yield have we stopped on the last execution. And also here we see x1, which is basically the local variable inside of the closure. We also have a closure type structure, which is basically two pointers bundled together. One of the pointers is the function pointer to the actual function which will be doing the work, and the other pointer is the pointer to the environment, to the state. And having this closure type, if you have an instance of a closure type, you can just call the function pointer from it, passing it the environment, and then the function which is actually doing the actual work will take the state from the state pointer and figure out how far along it has reached in the state machine of the resumable function and continue. Again, this compiles to C code. So NIM compilation to C and C++ is a big win because of a few reasons. The scope of the compiler is reduced greatly because we end up leveraging all of the optimizations in GCC, Clang, and whatever. We also don't have to think about code generation and register allocation and whatever. It also gives us support for a bunch of platforms out of the box. And this NIM is the language which has the easiest interoperability with C++ because it basically compiles to C++. And we'll see later how we can the two languages can talk to each other. One more thing. So whenever we define a module and it exports a bunch of symbols, we don't generate a header for it, which is later reused, because then everybody who uses that module would end up using, or at least having forward declarations of all of those modules, of all of those functions. As I said previously, each source file has the forward declarations of only whatever is necessary for it to work. And if you reference only a tiny bit of some other module, you're gonna forward declare only that tiny bit of that other module. And even the high-level macros and templates, all of them get crushed and, how do I say it, the final C code is not optimized for readability by humans, but it's mostly optimal code, and most of the zero-cost abstractions like macros and templates get really obliterated by the NIM compiler, and at the end we have the bare minimum of C code we actually need, which later the C compiler ends up optimizing even further. So how do the two languages talk to each other? There's this thing called the foreign function interface, and in NIM, we can easily say that if we want to use the printf function from std.io header, we can define it as a procedure in NIM, and we can say within these curly braces that it comes from that specific header, and we should import that specific symbol from C. And then we can use this printf function within NIM, and it will, if we use it, the compiler will make sure that it generates the include to the appropriate header which introduces it, and it will just remap the call. We also can put any C++ inside of NIM code and actually just tell the compiler, dump this as it is during the compilation phase. We can also say what libraries we want to link against or what other source files are necessary in order to link the entire thing. Also, we can make NIM code talk to, we can also call NIM code from C++. Suppose we have this fib.nim module, which defines a fib function, and it's annotated with export C. Now we can call the NIM compiler on that module and tell it, we don't want a main function, we don't want to link, we just want to generate a header. And after that, we'll have a C header, and that function will be callable from C. We can even interface with more complex types like templates, in this case, std map. We can also define our procedure to access elements and assign them stuff. And at the end, when we actually use these functions we have defined, the final generated C++ is literally what we would have written by hand in C++ anyway. So there are no intermediate layers because since one of the languages compiles to the other, bindings can be as optimal as they could be. And there are different tools which can automate the generation of bindings. One of them is C2NIM, and another is NIM2ROP. And if you're curious, again, all of these slides will be available at the end, and you're going to check out all the links if you're interested. NIM has a garbage collector. So well, there's a little bit more to the story. There are different garbage collectors which you can use. And in NIM, you can have a lot more control, unlike in other languages. Like, you can decide when the GC should run, and you can also tell it for how long it should run. Also, each thread has its own garbage collector, and they don't have to wait for each other in order to do their work. And the most important part is that the GC can be avoided, and it can even be turned off, even right now. So if we're dealing with simple objects and value-based types, destructors, stack and manual heap allocation, we can write code as if it's C++ in NIM. But only if we use ref object, which is here at the end. That means that those objects will be GC managed. And even in that case, we won't always have to deal with the GC. So if we create an object which is GC managed within a scope, but we never take a reference of that object outside of the scope, so no reference outlives that scope, we can clean it up right there, and we don't have to clean it up later with the garbage collector. So this is a graphic about the memory and time usage of NIM's garbage collector. The blue lines are the memory consumption. I'm not really sure how this measurement was done, but I would assume it's like a similar type of program with the different languages. But the more important part is the green bar, that in this case, NIM's GC has run for less than a millisecond, and we can even tune that. We can maybe make it run for even less time. Again, we have a lot more control than in any of these other languages. And also, NIM's binaries are quite small. This graphic is a bit outdated. I think NIM's binaries are now around 70, not 40K, but still it's much lower than all of the other languages. So yes, it has some runtime, yes, it has a garbage collector, but you can actually avoid it, and even if you don't avoid it, it's still perhaps the most optimal thing out there. So, the NIM backend. As we already talked, NIM can generate C and C++ code. In the case of C++, it can also reuse the exceptions in C++, and it can even interact with them. But it can also compile to JavaScript, and we'll see in a bit later why that's cool. Actually, I'm just going to tell you right now, if you're writing a web application and you have to write the backend and the client side, which runs in the browser, if you can do that in the same language, that's really, really powerful. I mean, the less languages you have to deal with, the less, the more you streamline things, the better. And even if you're compiling to C and C++, you can still target the browser with things such as WebAssembly or ASM.js. Even right now, you can compile normal C programs, including NIM programs, through C, which generate really optimal code, and have that run in the browser. So there are some modules which are only for the JavaScript backend, otherwise they're not allowed, for example, the DOM. And yeah, this is NIM code we can write. We can import the DOM and do anything with the document object model of the web application. So, a little bit about C++. I really love this meme because it's in every day with me. I guess this is the everyday life of any C++ programmer. Sometimes we have to wait for tens of minutes or even hours just to get a compilation. And a little bit about C++. C++ 20, huge release, really cool stuff, but it's even more complex than ever before. And people say that C++ is expert-friendly, but I say that it's expert-tolerable. I mean, they barely, in my opinion, tolerate it. In C++, it takes more than 5,000 lines of code to implement optional, which is basically a value and a Boolean. That's something which shouldn't take 5,000 lines of code and a bunch of mistakes and testing. And if we think that in each 1,000 lines of code, no matter the language, we always have the same amount of bugs, then we would want to reduce the amount of code we have. If a project is 100,000 lines of code, it's going to have many more bugs compared to 10,000 lines of code. Again, that's a not proven rule, but anyway. What else? In C++ 20, ranges are coming, but if you include the ranges header and write a 20 lines of code snippet, you end up compiling for 3 seconds, just because of all of those zero-cost abstractions. And if you actually decide to build in debug, all of those zero-cost abstractions won't end up inline at all. And actually, your debug builds will be perhaps 5, 10 times even much more slower than the release build. And for some applications, debug builds stop being an option at all. So it's my opinion that C++ is a huge mess. I mean, it's a really nice research project. We see a bunch of things, how they implement them, but we can learn from that. And instead of sinking more and more time and effort into such an suboptimal language, we can just use something better, which is here. And all it needs is more people using it. Some other problems, yeah, variant, again, discriminated unions in C++. It took them 3 years to design something, and it's still not really cool, and it's still a few thousand lines of code and whatever. In NIM, it comes by default. And yeah, a few interesting quotes, like 50 years of programming language research, and we end up with C++. I mean, whenever somebody says that C++ is fine, in my opinion, he hasn't encountered a really good language. And one quote I really like by Scott Myers is that he was once at a D conference, and he said the title of the talk was, "The last thing D needs is someone like me," because he used to be in the C++ ecosystem, and he was writing all of these effective C++ books just to explain how to not shoot yourself that much into the foot. Because C++ is really hard to use, and the goal of languages should be not to be that hard. And NIM can be thought of in comparison to C++ as CoffeeScript is to JavaScript. It's a better language which compiles to the stable platform. And yeah, demo, okay, I'll show you how much time it takes to compile the NIM compiler. This is the compilation in the NIM part. That's over, now we're compiling the C code, all of the modules. And we link them. 21, 22 seconds for the entire compiler. I mean, I want to see somebody build LLVM in 22 seconds on a single machine. A little bit of stats. This is the popularity of D based on GitHub stars. It's not a really good metric, but let's roll with it. It's pretty linear. What, that's 8, 9 years of development, 2,000 stars. This is Rust. Since 2010, now it has 40,000 stars. I really wanted to include a section about Rust, but I couldn't because of the time constraints for this talk. But still, we can see the trend. Rust is already a major language. But one really cool thing about NIM is that notice the curve in Rust. Look at it in NIM. It's a bit more curved in a different way. It has more momentum. It's growing faster. And even though it's only at about 8,000 stars, it's going to surpass Rust in, I don't know, 20 years. So that's it from me. I mean, version 1.0 of NIM is already out. There are a lot more interesting things which are upcoming. And get involved, choose NIM, if you have any questions.
Well, we do not have much time, so let's start quick.
Thank you for the nice talk. Well, with the risk to piss you off, I'm going to ask you 2 questions. So the first one is, what is your personal opinion for some of the language decisions in Rust compared to NIM, and specifically the borrowing and ownership, and also the direct compilation to to HHVM compared to compilation to C++ or C? And the second question is, because I'm a web developer, how good is the JavaScript ecosystem in NIM? And for example, can I use the protobufs and to build a full-fledged gRPC implementation for the browser? Compare that to the native JavaScript implementation?
Well, first I'll answer the second question. I believe you should be able to do that. And for the first question, in comparison to Rust, so NIM is already really much more secure than C and C++ because of a plethora of reasons. But even the lifetime and the ownership and borrow checker, it can be implemented in NIM as well. It's just that NIM is just a little bit further behind in that regard, but in terms of the actual language, is way beyond what Rust is capable of. And it would take time, but that could be implemented. NIM is already much safer than C and C++. And about the HHVM stuff, I'm not able to answer that, but I guess Zachary might have an idea. Sorry for putting you on the spot.
Okay.
Later, after the conference.
Okay, and it's time to stop now. So if you have some more questions, you can ask him now after we applaud him again.